Continuing along, let's get into this hybridization thing. So once again, I hope that this is more familiar stuff to you, but also I hope that I'm able to add some things that you didn't know before, okay? So let's do it. So the first hybrid orbital we're going to talk about is sp3, okay? And so here I've got my classic general chemistry notes up, right? We know from atomic carbon, it's a 2s2, 2p2, okay? And so we kind of, this is often viewed as a promotion and then a hybridization, okay? Although it's not quite really like it's promoting to an excited state, even though delta L is allowed to be plus or minus 1, that's fully allowed, right? For example, this 2s can shift up to the 2p. But again, it's not really like an excited state, like, you know, pumping energy into something and watching it promote to an excited state, okay? What this really is truly what we call hybridizing. And I'll get into what that's really, what is that more specifically meaning, okay? But in any event, if we kind of view this like this promote and then hybridize, our 2s2 gets promoted to this 2p3, and now we have 4 unpaired electrons, 1 in each px, py, pz, and 1 in 2s, as indicated as such, okay? And we view this as creating what's called a new orbital, a hybrid orbital, which is sp3, and it's literally because there's 1 s and 3 p's, okay? And so that kind of looks pictorially like something like this, where we can see an overlap of our s orbital with our p orbitals. And because of the confluence of constructive and destructive interference, right? Remember, there's positive regions, so there's the positive z, the positive x, and the positive y. We also know that there's negative regions. There's the negative x, the negative z, and the negative y. And so all of those various regions will interfere constructively and destructively to result in this new hybrid orbital shape that we all know and love as the sp3 with the 109.5 degree tetrahedron bonding arrangement. Okay, so hopefully that is what you remember, the review. But now, if we look at the new stuff, how we actually construct this through the process of quantum mechanics, that's right, hybrid orbitals are superpositions of atomic orbitals. And so this gets to be pretty intense. So let's put this all together. And so I'll remind you, right, our ket means wave function, right, just as a friendly reminder, okay? And here, so there's 4 new wave functions we're going to create, the H1, H2, H3, H4, and I've put this little vector notation right there to indicate that each one of these wave functions do end up with a direction-specific orientation. So for example, if I look at the H1 wave function, the H1 wave function is itself a superposition of 2s, 2px, 2py, and 2pz. So remember, each one of these would be the full wave function. And later on, coming up, I'm going to show you how we dissect all these wave functions, okay? And if we were to now look at then the magnitude, and not only I shouldn't say the magnitude, but the sign, right? We've created this superposition with all positive elements and our basis set. If we were to now graph this in our XYZ coordinate system, right? The positive px, the positive py, and the positive pz, and of course we know 2s has regions of positive and negative because it's spherically symmetrical about the origin, then what we would get is this H1 going into this positive coordinate region, right? So it's going to be all positive. Positive x, positive y, positive z. Okay? Well, what about H2? Well, now H2, we create negative elements in the px and the py, and still a positive element in the pz. And all of that order is just switched around in H3 and H4 to give us positive and negative permutations of each. And of course, we will need 2 of each, right? So if I look at px, I have 2 positive instances of 2px, and I have 2 negative instances of 2px. And same with 2py, and same with 2pz. Okay? And I don't need to do that with 2s, because remember, s is spherically symmetrical about the whole coordinate system. And so now if I were to look at that and draw those up, right, assuming I can draw this on this reasonable scale, I would now have still into the positive z, but now into the negative y and the negative x. So I'm going to draw that looking something like that, going back into that coordinate. And of course, if I did H3, now that's going to be into the negative z and the negative x, but in the positive y. And so that's going to look, let's see, something like that, right? It's going to go out into that direction. And then now, of course, the H4, the positive x and the negative y and the negative z, so that's going to make it go out something like that. So my shape looks really terrible. But all of those directions that I'm showing you, all of those vectors, would then have an angle of 109.5 between them, which is pretty cool, okay? And then so now when I take all of these basis sets and add them together, I now get the SP3 wave function. And what do you know? Look what I have right here to the right of me on Mathematica. So I know the font on this is kind of small. So actually, let's just go ahead and turn it up for just 1 second so that you can see it. So there we go, right? I've got that exact. So I'm not showing you the equations yet. We'll get there, okay? And I've also put this in an x, y, z coordinate system, which I'll describe in a minute. And I've done the x, y, z coordinate system for convenience so that I can get those directions. I can get those appropriate vectors, okay? And so now what's pretty cool is when I've got the, right, the SP3, I've got the linear sum of all of those. I've got the SP32, which is really to say like the H1, the H2, the H3, and the H4, right? All those different permutations. And then now I plot the sum of them. So I'm plotting them all, I should really say I'm plotting them all individually, okay? I'm not adding them together, but we know that the SP3 will be a superposition of all. But for best visual representation, if you look at them all individually, then we get something like this, which is pretty cool. And I haven't done, you know, I haven't measured the angle between these, but it's 109.5, okay. And what's also really cool is I'm seeing the negative regions of the wave function, which I've colored in red, and I'm seeing the positive regions of the wave function, which I've colored in green, to really show you that importance of the positive and negative regions, because that's what shows us all in those different directions. So this is pretty cool stuff, okay? So I'm going to make that a little bit smaller so I can shimmy that over a little bit. Okay, so moving along. And so if we kind of keep going with this here, there's another representation I'm going to show you with how we could kind of, where the shape is largely coming from. Obviously, we can use a computer to get it for us exactly. But if we look at the radial wave functions, so that's what I have right here, the radial wave functions. So I'll remind you, those are the R, N, L of R functions. So for example, when n is 2 and L is 0, that's R20, which is the 2s wave function, right? And when n is 2 and L is 1, that's the R21, that gives me the 2p wave function, the radial wave function. And so we note that the 2s, and this is not the square, right? We want to see positive and negative values. The positive and negative values of the wave functions are important in molecular orbital theory and in valence bond theory. Okay, so we can see the R2s. I'm going to highlight, right, that it drops down, it drops below, right, there's a node, and then it comes back up and it approaches the x-axis. And now the 2p, it's only positive regions, right? And it's kind of got this almost Boltzmann-like distribution. So let's keep that in mind, okay? And so now these two wave functions, they're flipped on their side 90 degrees, and they're added together. So let's take a look. So here, this blue is my 2s. And check it out. It drops down, it hits that node, it goes below, and reappears, okay? And so then that's just drawn symmetrically about this axis, right? Because we recognize that we can swing these radial functions around to, right, positive R values, or we can swing them around to negative R values. And so that's what's done on this graph right here, right? Then we can see the 2s wave function, but now as negative values, okay? So here's what's important to note, though. When we do the same thing for 2p, when I go and plug in negative R values for R21, it actually flips the sign. And I'll show you that. I don't have the equation in front of you, but I'll just show you that result. Where if suppose, well, it's kind of drawn backwards, but let's suppose that these are my positive values and these are my negative values, right? So here is my positive values of 2p, right? So it just kind of looks like that, that distribution, right? But now going to negative values for specifically the R21, it changes the sign of the function and looks something like that, okay? So now when we add those two things together, we're going to have regions of heightened constructive interference indicated right here, right? Because, and at this point, it doesn't really matter whether it's negative or positive. What matters is that they're both constructively interfering, right? They're both on this side of the axis. So that leads to a large lobe right there, okay? And on this side of the axis, they're on opposite sides, okay? And so the result is destructive interference, which is a much smaller curve that's drawn there. And so when you look at those two shapes, you get a really large lobe looking like this. That's all constructive interference. And you get a small lobe that looks like this. That's all destructive interference. And right, this bigger area right here, right, that was the negative region, and this bigger area right here, that's the positive region. And if you look at my Mathematica model, here I've specifically labeled red as the negative region and green as the positive region. So we can see that. We can see this larger negative region lobe and this smaller positive region lobe, okay? And of course we know that those are, right, the 109, technically 109.47, 109.5 is the angle we all know and love. And here this is only showing you one of those lobes as indicated in this picture, right? But those black lines, right, show you the vector where each one of those lobes would then exist, okay? As given by this guy right here, okay? Very cool stuff. So moving along, and finally, if I want to make a molecule out of sp3 hybridized carbon, okay? Now, finally, I have to have overlap of an empty hydrogen 1s orbital with an empty sp3 orbital. And interestingly, it ends up being the negative region of the wave function that overlaps. That then would have to overlap with the negative region of this wave function as well to give us the chemical bond, okay? Which is pretty cool. Because once again, we only had one electron where is it? Yes, 1 electron in each of the sp3s. So to make a bond, and specifically to make a sigma bond, right? Then we have that spherically symmetrical overlap. And so now, because this is not just a simple diatomic molecule, right? We get a coordinate system for each sp3 orbital where there's a hydrogen positioned. So for this chemical bond, right, the one that I'll highlight here, that represents a z-axis coordinate system for that particular one, okay? But if I look down this chemical bond, that makes another z-axis and another z-axis and so on and so forth. So that's where this gets really complicated, because when we put together wave functions for these molecules, we recognize that we have multiple coordinate systems based on our sigma bond, okay? Hopefully that makes good sense. So moving along, let's talk about sp2. So sp2 occurs when we still have this promotion, or excuse me, rather, I misspoke here. So sp2 happens when one of our electrons, one of our p electrons is left out, and one s and only two p's hybridize. So sp2, one s and two p's hybridize, and we've got one leftover p orbital, okay? That ends up looking something like this, where we've got our, one electron in each sp2, but then of course in the case of carbon, we will have one extra electron in that p orbital, whether it's the top or bottom lobe, okay? And if I look at my basis set, it looks something like this, and these are already normalized, and we're not going to normalize these, I'm just giving them to you, okay? And now if I scan down here, I've got my sp2 wave functions all drawn up, right? There's my 2s plus root 2 of 2py, which you can see there, 2s plus root 2 of 2py, and so on and so forth. And when I look at this shape now, look, it's planar. So if I hold it up to this axis, right, we can see that it makes a plane. And there's only 3 of those lobes. And if you look at this, you should recognize it's 120 degrees. Okay? Beautiful. So we can see that 120 degree bonding angle, right? And we also, right, there's going to be another one of those lobes right there, and then another one of those lobes right there, as indicated in my picture. Okay? And what about that empty p electron, right? Well, that p electron is primed for forming pi bonds because it's going to be off axis, right? Remember, if I want to make a bond from this sp2 hybrid orbital, I'm going to have, right, a z-axis going down this way or down the other two, and that empty electron in the p orbital right there is going to be off axis. So that's prime for making a pi bond. And so we can see that here with ethene, okay? So we recognize that each carbon is sp2. And here we can see the green sp2 orbitals, right? They are forming overlap through that internuclear zone. So that's my z-axis. So that makes a sigma bond, right, as shown right here. But now, right, remember I had one extra electron in that p orbital that was off axis. So that's perfect for making a pi bond, which is where we see in ethene a pi bond and a sigma bond. And additionally, we can draw up a new coordinate system for the carbon-hydrogen bonds, right? We'll have a z-axis for that sigma bond. We'll have another z-axis for that sigma bond, and so on, okay? And so finally, to wrap this up, sp, right? When only one s and one p electron hybridize. So that makes a very simple basis set. And it has to be Z for the internuclear axis, right, to make a sigma bond. And if I look at my Mathematica file, yep, you can see it's very simple. It's just psi2s plus psi2pz or psi-s minus psi2pz. And that makes my 180-degree linear sp hybrid orbital. And so now if we put together something like ethylene or acetylene, right? Then now what we should recognize here is when I go to look at this, okay, my sp hybrid orbitals, I'm going to now have 2 extra electrons left over in p orbitals, right? And so that's given right here. So if I'm looking at this acetylene, then I know I've got an electron here in the sp, and I've got an electron here in the sp. Those form together to make my sigma bond, right, down my internuclear axis. But now I've got an extra electron up here. I've got an extra electron up here. I've got an extra electron up here. And I've got an extra electron up here to form, oops, I drew those 90 degrees. So those should be right here and here, 90 degrees relative to each other, to give me 2 pi bonds and a sigma bond, which we know as the observed bonding. Okay, beautiful. So I'm going to cut that off, and on the very last lecture I'm going to record, this is going to be very quick, and I'm going to walk you through how we do an x, y, z coordinate system with valence bond theory. And that's what's going to allow us to create these lovely Mathematica simulations of the hybrid orbitals, which is the subject of part 1 for your Math 8 assignment. Okay, so the next video will be very short, just detailing how we can mechanically go through these equations and create these hybrid orbital superpositions. Okay, folks, I'll see you in the 3rd and final video on valence bond theory.